VMA operations. The VM ops field in the VM area struct structure points to the table of operations associated with a given memory area, which the kernel can invoke to manipulate the VMA. So this is again, these are sort of like methods to the VM area struct object. This is like, pretend this one is like the this in object-oriented languages. So anyway, the VM area struct acts as a generic object for representing any type of memory area. And the operations table describes the specific methods that can operate on this particular instance of the object. The operations table is represented by struct VM operations struct and is defined in linux/mm.h. So open, close, fault, page, mkwrite, access, all these methods are described now here. I've learned. So here's a description for each individual method. You'll have open. This function is invoked when the given memory area is added to an address space. Close. This function is invoked when the given memory area is removed from the address space. Fault. This function is invoked by the page fault handler when a page that is not present in the physical memory is accessed. So this will invoke the proper implementation. I think last time I didn't really make note of that, but of what would happen if a page fault occurs. Meaning that the piece of data is not in physical memory. So yeah, page mkwrite. This function is invoked by the page fault handler when a page that was read-only is being made writable. Then you'll have access. This function is invoked by the access process VM when the get user pages fails. So list of trees of memory areas. List and trees of memory areas. So as discussed, memory areas are accessed via both the mmap and mmrb fields of the memory descriptor. These two data structures independently point to all the memory area objects associated with the memory descriptor. In fact, they both contain pointers to the same VM area struct structures, merely represented in different ways. The first field, mmap, links together all the memory area objects in a singly linked list. Each VM area struct structure is linked into the list via its vmnext field. The areas are sorted by ascending address, so kind of similar to like the rectangle that we always draw, the memory map. So the first memory area is the VM area struct structures to which mmap points. The last structure points to null. The second field, mmrb, links together all the memory area objects in a red-black tree. The root of the red-black tree is mmrb, and each VM area struct structure in this address space is linked to the tree via its vmrb field. A red-black tree is a type of balanced binary tree. Each element in a red-black tree is called a node. The initial node is called the root of the tree. Most nodes have two children, a left child and a right child. Some nodes have only one child, and the final nodes called leaves have no children. For any node, the elements to the left are smaller in value, whereas the elements to the right are larger in value. Furthermore, each node is assigned a color, red or black, hence the name of the tree, according to two rules. The children of a red node are black, and every path through the tree from a node to the leaf must contain the same number of black nodes. So this has been mentioned before. It's actually something that's tricky to implement, so we don't really want to go into details unless we really have to. The root node is always red. Searching of insertion to and deletion from the tree is an O login operation. So keep in mind, since it's a red-black tree, it's a form of a balanced search tree, so it never goes too deep and degenerates to linked lists. So the linked list is used when every node needs to be traversed. The red-black tree is used when locating a specific memory area in the address space. So the linked list and the red-black tree are both used together depending on the operation we want to do. In this manner, the kernel uses the redundant data structures to provide optimal performance regardless of the operation performed on the memory areas. So memory areas in real life. Oh, this is going to be interesting. Okay, so let's look at a particular process's address space and the memory areas inside. This task uses the useful proc file system, so /proc file system, and the pmap utility. The example is a simple user space program which does absolutely nothing of value except act as an example. So he just has like a simple main here. So you know what? It's been a while since we programmed. Let's do something easy. This is easy. So we can just do this. So was it cd code? Okay. Memmap. Okay, let's just do that. So vim-main.c, just include stdio.h, include, actually that's all we need. Int main void, return 0. Then let's just do printf. Hello world. So a simple hello world program. Then we can do just main.c. And then, yeah, what do we do? Okay, so take note of the few memory areas in the process's address space. Okay, there is the text section, the data section, and BSS. Hold on. Assuming this process is dynamically linked with the C library, these three memory areas also exist for libc.so and again for ld.so. Finally, there is also the process's stack. So should we compile it? Should we make it a loop because it returns right away? Yeah, let's do that. While no, let's just do for. Yeah, this is while true. Let's just print a bunch of these, and that's not while one. There we go. So then, should I also? I should have tmux, right? I don't have tmux. Pacman sy tmux. Oops. Okay, there we go. Okay, so control B shift there. Okay, so this one is going to be my program running. Okay, and this one is going to be what the data that we're gonna find. So what do we need? So output proc PID maps. Okay, so if we do htop, a.out is what? 106698. 106698. So 106698, and there's it maps. Yeah, so let's wait. Yeah, so let's do cat that. Oh, look at that. Okay. How do I resize this? There we go. Okay. Let's do this. This height to less so that we can see what's going on here. Okay. Okay, so let's see what they're saying. So this is the C standard library. From this address to this address is this dynamic library loaded here. Then we see multiple of these. I think our code is probably up top here on these addresses. Notice how they're pretty far. It's probably the stack here, and then the heap starts here, I guess. And then, oh no, the stack is here, very low. Interesting. Okay. Sure. So the data is in the form of start to end permission. Oh, so read, write, and then what does P mean? What was this saying again? It has read, write. We'll see. Offset, I guess how big it is, major, minor, inode, and file. So here the stack is this big. Okay, it has read write permissions. I guess X is execute. Okay, so read write P, and I'm guessing since these are code sections, they don't have write or write sections. We just read and put it into memory. Sure. This one, oh, this one's execute right there. Okay, so this one must be the real program. Not too sure. Some of them might use global and constants. Okay. Oh, offset. Oh, okay. Cool. Oh, how did he get it to be like this? That's strange. PMAP. Oh, PMAP. Okay. PMAP. This is more readable. Okay, let's do that. PMAP 106.698. Oops, 698. Oh, that's better. Okay, let's do this less. Okay, 4K for our program, which makes sense because our program is super small anyway, and then a block is like 4K, and then the stack down here. Oh wait, no, it's not stack. Down here, stack is 132K. Sure. Cool. Anonymous memory means heap, from what I recall. And it looks like the C standard library is just only like maybe almost 2 megabytes total. In the loader, the dynamic library loader, it's right here. So, and these are all the addresses. Cool. Learn something new. Okay. Cool. So the first 3 rows are the text section, data section, and BSS of libc.so. The C library. The next 2 rows are the text and data section of our executable object. The following 3 rows are the text section, data section, and BSS for ld.so. Okay, so they all have their own like program code, data, and then I forgot what BSS was. What's BSS again? Block starting symbol is a portion of object file. Okay, so it's just a portion, some portion of the program. The last row is a processing stack. Note how the text sections are all readable and executable, which is what you expect for object code. On the other hand, the data section and BSS, which both contain global variables, are marked readable and writable but not executable. The stack is naturally readable, writable, and executable. Not much use otherwise. The entire address space takes up about 1,340 kilobytes, but only 40 kilobytes are writable and private. If a memory region is shared or non-writable, the kernel keeps only 1 copy of the backing file in memory. This might seem like common sense for shared mappings, but the non-writable case can come as a bit of a surprise. If you consider that a non-writable mapping can never change, meaning the mapping is only read from, it is clear that it is safe to load the image only once into memory. Therefore, the C library needs to occupy only 1,212 kilobytes in physical memory and not 1,212 kilobytes multiplied by every process using the library. Okay, makes sense. You want to just only load it once, and if you could just reuse it if it's not writable at all, I mean that's never going to change, it can only be read. Okay, because this process has access to about 1,340 kilobytes worth of data and code, yet consumes only about 40 kilobytes of physical memory. The space savings from such sharing is substantial. Yeah, that makes sense why. This is like a case for dynamically linked libraries for sure. Statically, it would have been loaded with the code. So note the memory areas without a mapped file on device 00 to 00 and inode 0. This is the 0 page, which is a mapping that consists of all zeros. By mapping the 0 page over a writable memory area, the area is in effect initialized to all zeros. This is important in that it provides a zeroed memory area, which is expected by the BSS. Because the mapping is not shared, as soon as the process writes to this data, a copy is made. I'll copy and write, and the value is updated from 0. Each of the memory areas associated with the process corresponds to a VM area structure. Oh, okay, so one of those areas, like one of these things here, will have a VM area structure. And I should probably quit this program. It's like, oops. Okay, cool. You know what? I should also open my system. I'm here. Sudo pacman syu. Okay. Okay, sure. Whoa, that's a lot. What do we have? Oops. Whoa. What do we have? Ah, come on. I usually use a different key binding. Come on, I can do this. Control B, control. There we go. Oh, it's like literally. Okay, whatever. I don't care what I'm upgrading. I know I have to upgrade a lot, so I'm just gonna do this. Okay. Okay, so anyway. Manipulating memory areas. The kernel often has to perform operations on the memory areas, such as whether a given address exists in a given VMA. These operations are frequent and form the basis of the mmap routine, which is covered in the next section. A handful of helper functions are defined to assist these jobs. These functions are all declared in linux/mm.h. Find VMA. The kernel provides a function called findVMA for searching for the VMA in which a given memory address resides. It is defined in mm/mmap.c. So struct VM area struct find VMA. Okay, so given this address and this memory map struct, we can just search for the corresponding VM area struct value or the pointer to it. So this function searches the given address space for the first memory area whose VMN field is greater than ADDR. In other words, this function finds the first memory area that contains ADDR or begins at an address greater than ADDR. If no such memory area exists, the function returns null. Otherwise, a pointer to the VM area structure is returned. Note that because the returned VMA may start at an address greater than ADDR, the given address does not necessarily lie inside the returned VMA. The result of the findVMA function is cached in the mmap cache field of the memory descriptor. Because of the probability of an operation on one VMA being followed by more operations on that same VMA, the cached results have a decent hit rate, about 30 to 40% in practice. Checking the cached result is quick. If the given address is not in the cache, you must search the memory areas associated with this memory descriptor for a match. This is done via the red-black tree. Okay, here we go. Okay, so this is the implementation. So this is the root node of the red-black tree, and we're just going to search down. And here we go. What we're comparing here, this is the important part, right? This is how we're searching. Since we want efficient searching for something specific, one of the values that an RB node will have is going to be the memory address. So we're going to compare the memory address. If the memory address of the current node is greater than the address that we want, then we're going to move left, because that's anything less than in the binary search tree. And then anything else right or greater than, so basically your address is greater than whatever the node is for the VMN, you're going to move right. Okay? So you do that, and then so you're just going to modify this RB node. And then what else happens here? So given that, if it's equal, so where's equal? Right here. So here, if we find that it's equal, okay, so we're every time we're doing we're moving left, if we find that now we finally hit something that's equal, we'll set the let's do it. VM area struct pointer to be the one that we have found. Okay. So now if we have that, then we're just going to point this mmap cache to this VM area struct and then return it. Okay, so find VMA prev. The find VMA pre function works the same as find VMA, but it also returns the last VMA before the ADDR. So it's basically this where we set here is going to be from the last iteration. So yeah, the function is also defined in mm/mmmap.c and declared in linux/mm.h. Okay, so the pprev argument stores a pointer to the VMA preceding ADR. So you need to pass in how you want to store that pointer. Find VMA intersection. Okay, the find VMA intersection function returns the first VMA that overlaps a given address interval. The function is defined in linux/mm.h because it is inline. Okay, and the first parameter is the address space to search. Okay, start ADDR is the start of the interval, and NDDR is the end of the interval. So right here, these two. As I say, it's essentially doing find a VMA. Okay, so internally, it's just using the same APIs. So obviously, if find VMA returns null, so would find VMA intersection. If the find VMA returns a valid VMA, however, find VMA intersection returns the same VMA only if it does not start after the end of the given address range. If the returned memory area does start after the end of the given address range, the function returns null. mmap and do mmap, creating an address interval. Where were we? Right there. Okay, let's make that 200. Okay, so the do map function is used by the kernel to create a new linear address interval. Saying that this function creates a new VMA is technically correct. It's not technically correct, because if the created address interval is adjacent to an existing address interval, and if they share the same permissions, the two intervals are merged into one. If this is not possible, a new VMA is created. In any case, do mmap is the function used to add an address interval to the process's address space, whether that means expanding an existing memory area or creating a new one. The do mmap functions is declared in linux/mm.h. I have a feeling this is probably used also to grow the heap, most likely. This function maps the file specified by file at offset for len. The file parameter can be null and offset can be 0, in which case the mapping will not be backed by a file. In that case, this is called an anonymous mapping, so memory mapping. So blank memory to so virtual addresses for physical RAM, since it doesn't exist on disk. If a file and file offset are provided, the mapping is called the file back mapping. The ADDR function optionally specifies the initial address from which to start the search for a free interval. The propt parameter specifies the access permissions for pages in the memory area. The possible permission flags are defined in ASM mman.h and are unique to each supported architecture, although in practice each architecture defines the flags listed in table 15.2. So prot read, prot write, prot x, prot none. So that's probably the same thing as these VM area permissions. Okay. So the flags parameter specifies flags that correspond to the remaining VMA flags. These flags specify the type and change the behavior of the mapping. They are also defined in ASM mm.h. See table 15.3. So we have map shared and all these other ones. I'm not going to say it. Too much. So yeah, it just defines what the mapping can do at a more granular level. Anyway, so if any of the parameters are invalid, do mmap returns a negative value. Otherwise, a suitable interval in virtual memory is located. If possible, the interval is merged with an adjacent memory area. Otherwise, a new VM area structure is allocated from the VM area cache peak slab cache. And the new memory area is added to the address spaces linked list and red-black tree of memory areas via the VMA link function. Next, the total VM field in the memory descriptor is updated. Finally, the function returns the initial address of the newly created address interval. The do mmap functionality is exported to user space via the mmap system call. The mmap system call is defined as this. So void mmap2 start length prot flags and whether or not it's file backed. Okay, and more offset. Okay, So this system call is named mmap2 because it is a second variant of mmap. The original mmap took an offset in bytes as the last parameter, and the current mmap2 receives the offset in pages. This enables larger files with larger offsets to be mapped. The original mmap, as specified by POSIX, is available from the C library as mmap, but is no longer implemented in the kernel proper, whereas the new version is available as mmap2. Both library calls use mmap2 system call, with the original mmap converting this offset from bytes to pages. Okay. Ooh. munmap and do munmap, removing an address interval. The do munmap function removes an address interval from a specified process address space. The function is declared in linux/mm.h do munmap with the memory map and then the start of that and how much you want to remove. Okay, so the first parameter specifies the address space from which the interval starting at address start of length len bytes is removed. On success, 0 is returned, otherwise a negative error code is returned. The mmap system call is exported to user space as a means to enable processes to remove address intervals from their address space. It is the complement of mmap system call. So int munmap void start size t length. The system call is defined in mm/mmap.c and acts as a simple wrapper to do munmap. So this is the implementation. It's very low level. Okay. Page tables. So although applications operate on virtual memory mapped to physical addresses, processors operate directly on those physical addresses. Consequently, when an application accesses a virtual memory address, it must be converted to the physical address before the processor can resolve the request. Performing this lookup is done via page tables. Page tables work by splitting the virtual address into chunks. Each chunk is used as an index into the table. The table points to either another table or the associated physical page. In Linux, the page tables consist of 3 levels. The multiple levels enable a sparsely populated address space, even on 64-bit machines. If the page tables were implemented as a single static array, their size on even 32-bit architectures would be enormous. Okay? Linux uses 3 levels of page tables even on architectures that do not support 3 levels in hardware. For example, some hardware uses only 2 levels or implements a hash in hardware. Using 3 levels is sort of the greatest common denominator. Architectures with a less complicated implementation can specify the kernel page tables as needed with compiler optimizations. So the top level page table is the page global directory, PGD. So this is the PGD here. And I'm guessing this points to different types of tables. Okay, PGD would consists of an array of PGD-T types. On most architectures, a PGD-T type is an unsigned long. The entries on the PGD point to entries in the second level directory, the PMD. Okay, so the PMD are the multiple page tables most likely. So, and the final level is the entries. So the final level is called simply the page table. The final level is called simply the page table and consists of page table entries of type PTE. Oh, okay, so these are the page entries. This is the multiple page tables. And what's the other one? Oops, are these ones for like specific? Weird. Okay. Okay, the kernel must set things up, however, in such a way that the hardware is happy and can do its things. Diagrams of the flow to virtual physical address lookup using page tables. Sure. I hope they're going to go in detail because second level directory. So global directory, an array of PGD-T types. So page tables or page directories you have a global directory, and then you have a local directory, and then that points to page tables, and then each one of these has page entries, which then leads to a physical page. Sure. Physical page meaning like a page of group of like 4 to 8 kilobytes in physical memory. Okay. So each process has its own page tables, threads to share them, of course. The PGD field of the memory descriptor points to the process's page global directory. Manipulating and traversing page tables requires a page table lock, which is located inside the associated memory descriptor. Page table data structures are quite architecture dependent and thus are defined in the ASM page.h. Because nearly every access of a page in virtual memory must be resolved to its corresponding address in physical memory, the performance of the page tables is very critical. Unfortunately, looking up all these addresses in memory can be done only so quickly. To facilitate this, most processors implement a translation look-aside buffer, or simply TLB. And that acts as a hardware cache of virtual to physical mappings. When accessing a virtual address, the processor first checks whether the mapping is cached in the TLB. If there is a hit, the physical address is immediately returned. Otherwise, if there is a miss, the page tables are consulted for the corresponding physical address. Nonetheless, page table management is still a critical and evolving part of the kernel. Changes to this area in 2.6 include allocating parts of the page table out of high memory. Future possibilities include shared page tables with copy and write semantics. In that scheme, page tables would be shared between parent and child across a fork. When the parent or the child attempted to modify the particular page table entry, a copy would be created and the two processes would no longer share that entry. Sharing page tables will remove the overhead of copying the page table entries on fork. In conclusion, in this suspense-laden chapter, we looked at the abstraction of virtual memory provided to each process. We looked at how the kernel represents the process address space via struct struct, and how the kernel represents regions of memory within that space, struct vm area struct. We covered how the kernel creates basic memory maps via mmap and destroys via munmap. So I really think that malloc and free uses these underneath the hood. These memory regions. Finally, we covered page tables. Because Linux is a virtual memory based operating system, these concepts are essential to its operation and process model. The next chapter covers the page cache, general in-memory data cache used to fulfill all page I/O, and how the kernel performs page-based data write back. Okay, more memory stuff next time. Okay, thanks.